We're going to do an optimization example where we find the maximum and minimum vertical distance between two functions. Maximum and minimum vertical distance between functions. Okay? So the particular problem we're going to do is find the max and min distances, vertical distances. Find the max and min vertical distances between the parabolas. Find the max and min vertical distances between the parabolas. Let's say y sub 1 equals x squared minus 4x plus 7, and y sub 2 equals negative x squared plus 3. So we're trying to find the max and min vertical distance between these two curves, these two parabolas. Specifically though, when x is greater than or equal to 0 and less than or equal to 3. Okay, so clearly an optimization problem. We're trying to maximize and minimize in this problem. So we need to figure out how to calculate the vertical distance between two functions. And then we're going to look to maximize that distance function and minimize that distance function on this closed interval. Now, these are parabolas, so you should be pretty familiar with them. This parabola, because the coefficient of x squared is positive, is going to open up. And this parabola, because the coefficient of x squared is negative, means it opens down. In other words, this function is going to be opening up, and the second one's going to be opening down. So we could think of this as being the higher function. So when we calculate vertical distance, that's going to be important to keep in mind. All right, so in this particular optimization problem, we don't need to define any variables because we've already got all the variables we need. Furthermore, we don't need to define the relationships between x and y because those are given to us as well. So we can jump right to the function that we want to maximize and minimize. And so that's our vertical distance function, which I will call d. So d is the vertical distance between the two functions. If you want to calculate vertical distance, let me turn my auto zoom off. Okay. If you want to calculate the vertical distance between two functions, you take the top y value minus the bottom y value. And as I said before, this first function is higher than the second function in a way because it opens up and the other one opens down. So eventually this guy is going to be higher than that guy. So what I'm going to do for my distance function, I'm going to take y sub 1 minus y sub 2. And the problem with this is with any optimization problem, the function you create needs to be in terms of one variable. So luckily for us, I can rewrite y sub 1 using x, and I can also rewrite y sub 2 using x. So I'm going to do that replacement now. Y sub 1 is x squared minus 4x plus 7, minus y sub 2 is negative x squared plus 3. And so then I'll simplify this function a little bit by distributing my negative and combining like terms. So I've got x squared plus x squared giving me 2x squared. Then I have negative 4x, and I have 7 minus 3, which is positive 4. Okay? And so this is the function that we want to find the maximum and minimum of on the interval from 0 to 3. In order to do that, I need to find its critical numbers. So I'll look for d prime, which will be 4x minus 4. And so the critical number you can see is if this is 0, x would have to be 1. If you don't see that, solve that equation, 4x minus 4 equals 0. So the critical number is x equals 1. And good for us, this critical number lies in this closed interval, so that's useful. If it didn't, we would ignore it moving forward, and we would only look at the endpoints of this interval by the extreme value theorem, which guarantees an absolute max and an absolute min on a closed interval for a continuous function at the endpoints or at critical numbers. If the critical numbers aren't in the interval, the max and min have to happen at the endpoints. But what we're going to do now is, because of the extreme value theorem, I don't have to look at my first derivative and find out where the function d is increasing and decreasing, because I know that I need to test x equals 1, x equals 0, and x equals 3. So if x equals 0, we're trying to find the maximum vertical distance. So I'm going to go back to my distance function, which is here. So if x equals 0, d equals 0 minus 0 plus 4. So the distance there is 4. If x equals 1, then I get 2 minus 4 is negative 2, plus 4 is 2. And finally, if x equals 3, then I get 2 times 9, which is 18, minus 12, which is 6, plus 4, which is 10. So find the maximum and minimum vertical distances between the parabolas. Well, the minimum is 2. So 2 is the minimum vertical distance, and 10 is the maximum vertical distance. Okay? So this one was kind of nice because it was on a closed interval for a continuous function, so we were guaranteed by the extreme value theorem to attain an absolute max and an absolute min. If we didn't have the closed interval, we would have to set up a chart where we look at, so we'd look at x, we'd look at d prime, and we'd look at d, right? We'd cut that at the x value 1, and we'd look at all x values less than 1 and all x values greater than 1, and use the increasing and decreasing behavior of the function to determine max and min, okay? But since we had a closed interval, we could bypass all that, go straight to the extreme value theorem.